Hey guys. All right, this is the 4-3 notes connecting f prime and f double prime with the graph of the original function. Okay, this might get kind of long, so there might be a few videos, which will be obvious, of course, on the YouTube. So just keep in mind I may have to stop this if it gets a little too long. All right. So, first derivative test for extrema. We've already determined that relative extrema occur at critical points. Hopefully that sounds very familiar to you. The behavior of the first derivative before and after those critical points will help determine whether or not the function has a relative maximum or relative minimum, or neither, at these critical points. So we're going to look at the first derivative before and after those critical points. All right, example 1, given the graph of f below, label the relative extrema. All right, so if this is the graph of the function, just f, where are the extrema? The relative extrema. Well, that's pretty easy to see. There's the relative max, and down here is the relative min. I think that was pretty easy. All right, let's look at the next question. Use the graph of f up here to do the following. Sketch f prime as accurately as you can and label the x values of the extrema from f on f prime. All right, so what we're going to do, try to make my marker a little different here. I'm going to go to red. All right, so this is our f prime graph right here, the derivative graph. Well, at this point right here where I drew this relative maximum, the derivative at that point is 0. Agreed? So come down here, and that means on the derivative graph, we're going to cross the x-axis at that point. Now, same thing for right here. We're going to have a 0 at that point right there. All right, so we're still graphing the derivative, which means slope. So what is the slope through this part of the graph? Well, it's a positive slope and it is approaching 0, so that means it's coming in something like this. What is the slope through this middle part of the graph? Well, it leaves 0, goes negative, stays negative, but then approaches 0 again, so it actually looks something like this. And then what happens after the relative minimum? Well, the graph goes back to a positive slope or a positive derivative, so it looks something like this. All right, let's look at the next page. The first derivative test. Let f be a continuous function and let c be a critical point. So c is somewhere that either the derivative is undefined or somewhere that the derivative is equal to 0. If f prime, the derivative, changes sign from positive to negative at c, then f has a local maximum value at c. All right, I'm going to go back to our picture here, and I'm going to read the same thing I just read a second ago. If f prime changes sign from positive, let's see if I can highlight. If f prime changes sign from positive to negative, that's what happened right there, then there is a local maximum value at c on the original function. Here is the point at which the derivative changes sign. It correlates back up to a relative maximum value on the function graph. Okay, look at number 2. We're on number 2 right here. Okay, number 2 says if f prime changes sign from negative to positive, well, that happens through here, from here to this part, right? That is where the derivative changes sign from negative to positive at c. Then f has a local minimum value at c. So come back up here. There is clearly a local minimum value at that place right there. And number 3 says if f prime does not change signs, then there is no local extreme value at c. Now keep in mind, everything we're doing right now are local or relative values, okay? They're not absolute maxes, they're not absolute mins, they are relative or local. Okay, this kind of goes to what I was just saying. If you are asked to find the absolute maximum, or if the word, or sorry, if just the word maximum is used and they don't say absolute maximum, if they don't say absolute maximum and they just say maximum, then they mean absolute maximum. Okay, the only time you are ever asked to find local or relative extreme, you will be told local or relative. Okay. Anyway, if you are asked to find the absolute maximum of a function on a closed interval, you must test the endpoints also. And it may be just as simple to plug in the endpoints and the critical points. Okay, everything we're learning right here in this lesson, the entire 4.3, are kind of like shortcuts, okay? You can always go back, take the first derivative, find the critical points, find your endpoints, and plug those into the equation. It's just sometimes that's really messy, and sometimes it's just flat out unnecessary for what you're being asked about the function. Okay, so we've already done this. That's what we did as I went back and forth between the pages. Let's look at example 3. Find where the function h of x equals x to the fourth minus 4x cubed is increasing and decreasing. Then use the first derivative test to determine any local extrema. Local, relative, not absolute. All right, let's see. So what's the first thing I need to do? Well, this is a first derivative test. So obviously I need to find the first derivative. So we'll find the first derivative, which will be h prime of x equals 4x cubed minus 12x squared. How do we find the extrema? Well, we look for where the first derivative is undefined, which is nowhere. It's fine. There's nothing going on weird with this graph. And then we also set it equal to 0. So let's do that. So 4x cubed minus 12x squared equals 0. What can I factor out? Let's see, I can factor out a 4x squared, and I get x minus 3 here. And then when I set each of these individually equal to 0, I get x equals 0 and x equals 3. Okay, so those are my critical points. Now, to do the first derivative test, I'm going to go back just a second. I need to find where the derivative changes sign from positive negative or negative positive. So in order to find where the first derivative changes sign, I need to create a sign chart. So, or sign graph. And it's really unnecessary to put those arrows on there. In fact, I don't like that, so I'm going to erase them. There, that's better. All right, this is a derivative. Mark it as a derivative. Sorry, we're in h, not x. Mark it as a derivative. That way you won't forget. And when you think about plugging values in, you won't think to plug values into the original function. Okay, so where are we testing? We're testing at 0 and at 3. You can look at this all different ways. I'm just going to do it the quick way, or I guess it depends on the equation whether one way is quicker than the other. In my opinion, I look back at the function and I say, well, 4x cubed minus 12x squared, that really doesn't have a whole lot going on. There are only 2 places to test. Well, okay, 3 places to test. So I'm just going to plug values in and look at what I've got. You can do it the other way, and in fact, I might show you a different way to do it tomorrow as well. Okay, so let's look at above 3. If you take anything bigger than 3 and you plug it in here, say you plug 1,000,000 in, you have 4 times 1,000,000 cubed minus 12 times 1,000,000 squared. Well, 1,000,000 cubed is so much bigger than 1,000,000 squared that this is going to be positive, no matter what you plug in, over the number 3. When you plug in a number between 0 and 3, say, just pick 1. I don't know, how about 1? If you plug 1 in, you get 4 minus 12. Well, that's negative. Now, if you plug a negative number in, negative number squared is still a negative number. A negative number did I say that right? A negative number cubed is still negative, and a negative number squared is positive. You have a subtraction sign here. Anyway, I'll quit talking. That's negative. Okay, so what is happening with the slope? Remember, this is the slope at these places. Well, when the slope is negative, the graph is decreasing. All right. So what does that tell us as far as the first derivative test? Well, we were asked to find where the function is increasing and decreasing. We've done that. Check. And we were asked to find any local extrema. Okay, well, we found the critical points, but in order to find whether they were an extreme value, a absolute max or absolute min, we would need to plug them back into the original equation and get numbers. Well, there's an easier way to do that. Just look at this information right here. Okay, go back to our first derivative test information. If f prime changes sign from positive to negative, or if f prime changes sign from negative to positive, what we're going to do is look for where that happens. So where, using this chart right here, where does the derivative change signs? Well, the only place the derivative changes signs is at x equals 3, because here it's decreasing, goes to 0, still decreasing, goes to 3. Ooh, now it's increasing. All right, so how are we going to summarize this in an answer? We would say something to the effect of, at x equals 3, h prime changed from negative to positive. Therefore, okay, what does this say? At x equals 3, h prime, the derivative, changed from negative to positive. Therefore, there is a relative minimum when x equals 3. Sorry, I'm having trouble breathing here. Therefore, I might even say, therefore, there is a relative minimum on h, on the original function, when x equals 3. All right, let's look at the next problem. Number 4, find where the function g of x equals x squared times e to the x is increasing and decreasing, and find any local extrema. Okay, so first thing we need to do is find the derivative. I hope you recognize that x squared times e to the x is a product rule. So we would have the first one times the derivative of the second one. Derivative of e to the x is just e to the x, plus the second one times the derivative of the first one. All right, now we need to set this equal to 0 to find our critical points. There is actually nowhere that it's undefined. If you don't believe me, put this into a graphing calculator. So if you put it, or if you set it equal to 0, let's see, you get 2x e to the x plus x squared. Oops, that's not right. X squared times e to the x equals 0. What can I factor out? That always makes things easier. Well, I can factor out an x e to the x, and I end up here with 2 plus x. All right, now when I take all three of my factors and I set them equal to 0, I get, there's 3 of them, right? Because it's x times e to the x times 2 plus x. So if x equals 0 right here, then my whole thing goes to 0. That's good. If x equals negative 2, my whole thing goes to 0. And that's what I want, right? Now, what about when e to the x is 0? Well, that would work. If e to the x was equal to 0, then the whole thing would actually turn into 0 because you'd have x times 0 times something else. But there is actually no place where e to the x is equal to 0. Think about it. If x is 0, you have e to the 0, which is 1. If x is any number besides 0, then you have a number. You have 2 point something something raised to a power. So there is nowhere that e to the x is equal to 0. So this is kind of a, it doesn't affect anything. Let's put it that way. It's not going to change anything for us, and it is certainly not a critical point that we need to consider in our sign chart. Okay, sign chart, let's see. We have 2 places to put on our graph here. We've got negative 2 and we have 0. As always, we need to label this as a derivative, okay, so we don't forget what we're doing. Now, I guess I'll do this one the other way. In this case, we need to list our 3 multiplied terms over here. So we have x, we have e to the x, and we have 2 plus x. X is anything bigger than 0, x is going to be positive. Anything between -2 and 0, x is going to be negative. And anything less than -2, x is going to be negative again. All right, how about e to the x? Well, e to the x is positive for anything bigger than 0. Even if you put a negative number in here, you end up getting a positive result. Whoops, positive. And if you put anything smaller than -2 in, you still get a positive result. How about x plus 2? Did I mess that up? Is it? Oh, I have 2 plus x, but I guess it really doesn't matter. X plus 2 and 2 plus x are the same thing. So if you plug anything bigger than 0 in here, you get a positive number. If you plug something between -2 and 0 in, you still get a positive number. And if you plug anything smaller than -2 in, you get a negative number. Okay, so here we have, sorry, negative times positive times a negative, that ends up being positive. In this interval, you have negative times positive, that is negative. And over here, you have positive times positive, which is a positive. Okay, so if the function is, or I'm sorry, if the derivative is positive, that means the function is increasing. If the derivative is negative, we're decreasing. And if the derivative is positive, again, we are increasing. Okay, so let's sum this up again using our local extrema. So we've kind of talked about the increasing and decreasing, but we need to write it all out and say where we have local extrema. Okay, let's see. I would write something like this. Since g prime, remember we're using the first derivative test here to find the extrema. Since g prime changes sign at, well, where does g prime change signs? Well, here it goes from a positive to a negative, changes signs there, and then from a negative to a positive. So it also changes signs there, so we have 2 different places to talk about. Since g prime changes sign at, we'll start with x equals -2, there is a wait, let's see, at g equals -2, I'm sorry, at c equals -2, is that a local min or a local max? Well, if we're going from positive slope to negative slope, that means we're going positive slope increasing to negative slope decreasing. What does it look like we have? We have a maximum, right? So that is indeed a local max. And, excuse me, when g prime changes sign at x equals 0, what do we have there? I'm going to go ahead and write it. We have a local min. But let's look at what happens. As you're coming up to 0, you have a negative slope, which looks something like this. Or you are decreasing. Negative slope, decreasing function. Looks something like this. And then at 0, the slope becomes positive and the function is increasing. So we turn right back around like this. So clearly we have a local minimum at that point. All right, let's keep going here. Actually, I'm going to stop the video here and just do concavity separate so that I can have not quite so long videos. All right, I'll see you in a second, or I'll talk to you in a second. Come back.